Okay, so hello everyone. Welcome to episode 55 of the Warsaw Quantum Computing Group Meetup. My name is Pavel and I will be the host of this meeting. And today we have pleasure to host a great speaker, Jakub Bliźniuk from Warsaw University of Technology. And he will tell us about post-quantum cryptography, keeping secrets in the post-quantum world. Before we start, we would like to thank our strategic partners, Cogit's, Starto, Sonovero R&D, and FinQubit. So actually, FinQubit has recently joined as our next strategic partner. And we would also like to thank our honorary partners. So there's also one new honorary partner here, Harrington Technology. And So before I give a voice to Jakub, maybe just an announcement or also a question to Jakub. Jakub, would you like to have this meeting interactive so that the participants could
Yeah,
interrupt and
no
ask
problem. I
questions?
don't have
Okay.
problem with questions in
Yeah.
the middle.
All right. So if there are any questions, please just raise your hand and we'll try
Hopefully I'll
to
see it.
interrupt. And yes, or I will try to interrupt. And as usually, there will be a Q&A session at the end. So you can also post your questions on our chat and we can ask the questions at the end. All right, I will now stop sharing my slides and Jakub, you can start sharing your presentation. So once again, thanks for accepting our invitation and the Zoom is yours.
Uh, so let's start with a brief introduction. I'm a student at Warsaw University of Technology, and this is mostly my hobby, something that I got uh, the effects of quantum computing on security and quantum cryptography in particular is something that I got really interested in a few years ago when I started my quantum journey. Uh, but in general, it's a field that I feel draws a lot of interest in the media because, well, as uh, as you can see, one use of quantum computers that you can find in headlines surprisingly often is breaking encryption. That is destroying our ciphers. Some will even claim that it will destroy all privacy and security. The quantum computers will destroy all privacy and security in the future. But well, is it that bad? Considering that I'm not holding a presentation titled "Quantum Computers Will Break All Security." It's probably not that bad, but that doesn't mean there isn't an issue. So let's start with agenda. To first get into post-quantum cryptography and everything, we'll start with a bit of context for classical cryptography before quantum computing, and especially RSA because it's the algorithm that's most in danger of being attacked. Then we'll go through quantum attacks and what they mean for RSA, ECC, and other cryptography. Then we'll get into the post-quantum part. That is, what algorithms are there? How do they work, and why do they work? And then a bit about some newer attacks on RSA, especially because it turns out this field has somehow started growing recently. And finally, a short conclusion. So, what is RSA anyway? If you think about encryption, probably your first thought is something like this. You have a key that you use some magic operation with to create a ciphertext that's essentially random, that no one can read, send it over some insecure channel that you don't trust, so that you assume that someone malicious might intercept in the middle. And the person on the other side uses the same key to decrypt it and read the original content. The issue is how do you get the key to the other person? Uh, this is the hard part because you can send it over the insecure channel and like you can do things like meeting in person, but that's obviously not really convenient. If you had to meet everyone you want to communicate on the internet with in person, just to provide the security of this communication, it would be absurd. So there are a few methods that do guarantee a secure channel for a small amount of data. And surprisingly, there is also there are also some quantum methods for key exchanges. But we won't be focusing on that. Instead, a few decades ago, we came with a different concept that is asymmetric encryption. Instead of having one key that we have to share over, we have to find a way to share between ourselves. We have two keys. One of these is shareable. We can just give it away publicly, post it on our profile, post it on some key server. And the other is the private key. This one is only for us. We're not sharing it anywhere, and it stays secret. So what changes with asymmetric encryption is that now we have two operations with two different keys. So encryption will usually happen with a public key, then we'll send the encrypted data, then we'll decrypt with the private key, and it doesn't work the other way around. However, in many schemes, you can actually do the totalopoly, that is encrypt with a private key, and then the private key doesn't decrypt, but the public key will. This is called signing, and it's how quite a lot of things are done nowadays. So RSA is one of the oldest public key systems. It was first developed actually in 1973, but that was for military use. I mean, it wasn't published anywhere, and then it was completely separately discovered and published by Rivest family in 1976. And it's extremely common. As mentioned, it can be used for encryption and signing, which is actually guaranteed for all of these schemes. And usually what ends up being encrypted is the symmetric key. That is because these crypto systems, like they provide a bit more flexibility, but on the other hand, they're quite a bit slower. So for example, if you want to do full disk encryption, you will prefer to use a symmetric algorithm and keep the key somewhere locally instead of using RSA everywhere, just because it's so slow. And as mentioned, signing is just to verify that the data comes from someone who possesses a private key. So the best example of usage of RSA and cryptography in general is probably TLS, because that's how all websites are secured nowadays. You basically exchange a few messages to create a session key that will be used for symmetric encryption, because again, symmetric encryption is just so much faster. So you don't want to encrypt everything with RSA. But because you have also the ability to sign, the public encryption is also used to verify the server. That is, we have an entire infrastructure of certificates that validate that the server is what it claims to be. Well, it's a bit harder than that in practice, because obviously, if you see a green lock, it doesn't mean that the site is good. It just means that your connection between you and the site is secure. And someone attested that this domain is hosted on this server, essentially. And other uses will include email encryption. Basically, it's still the most common algorithm used for PGP, SMIME, and even some modern attempts like Tutanota, though I think they're implementing post-quantum encryption now. And also document signing, because we're living in a more digital society. We're seeing a lot more things that can be done digitally, and we actually need to confirm when we do something that we're the actual person who did it. So for example, ID cards have embedded certificates. We have qualified certificate in Poland, and also EPWAP. All of this is based on RSA certificates mostly, and these are all used to attest that the person doing the action is who they claim to be, and that they wanted to actually do this action. also, quite importantly, usually for specially qualified certificates or ID cards, the keys themselves are not supposed to be possible to easily, like, maybe not possible, but not practical to extract from the device. So they're literally private keys. Not even the owner can get the key itself. It just sits on the device. So how does it work? Let's go through it from a bit of simple angular, the key generation. First, we choose two very large prime numbers. So just numbers that don't have any divisors over themselves and ones. There are actually a few other rules for these prime numbers, but that's implementation details essentially, one for security. Then we compute their product, so just multiply them together. And then we compute a Carmichael function of this multiplied together number. What this function does isn't that important for us. What's important is that it neatly decomposes. That is, the Carmichael function of a product of two numbers is actually the least common multiple of Carmichael functions of these products. And for primes, the Carmichael function is just the prime number minus one. So since we know these prime numbers at this point, computing this function is trivial. We literally just find least common multiple of these two numbers, which usually will be quite easy. And then we choose a random integer that will be coprime with, not actually random, just there are also some rules for E. It has to be coprime with the Carmichael function, so it can't have any other divisors other than one together. And then we compute module that is modular inverse of under the Carmichael function. And that's how we get our two keys. The private key, which is our number n, and the number d, and our public key, which is n and the e. So without getting into the encryption itself, we know that we have n and e because, well, it's the public key. It's the one that attackers are supposed to be able to get. And we want to find the number d because this is the secret. If we have it, we know that we'll be able to decrypt whatever. However, the encryption decryption works. We know that if we have the private key, we will be able to decrypt the message. So we know that this is equal to calculate if we know both P and Q, but the Carmichael function is actually really hard if we know only the product. So if we just can factor n, we know that it's a product of two primes, so it will have to be, so these are two unique factors. So we just have to find one factor, and we'll find the number n. We'll find the numbers p and q, just by dividing n by the one we find. So as long as we can find a number that divides n, like a whole number, just to be clear, an integer, we will find both p and q, and we will basically solve the whole problem because we'll be able to trivially calculate the Carmichael function and as such also d, and get the entire private key. Right there. Some people are writing the cat, sorry. Oh, okay. The relevant questions. So, how do we factor integers? Well, naively, we can just try dividing our number by everything that's smaller. We can optimize it somewhat because we know a bit about n. We only actually need to check the square root of n because if square root times anything bigger will be bigger than n, and square root times itself will be n. So if square root is an integer, it will be trivial, but it probably isn't. And because that would obviously mean that both of our primes are the same number, which would be obviously bad. And if you get two identical primes in the RSA, you really did something wrong. We only actually need to check two and other numbers, since if it would be divisible by 4, we know that it will also be divisible by 2, and it also has it only has two factors because it's a product of two primes. So we can rule out any even numbers. And as mentioned, we know that we're looking for exactly two factors, so we only need to find one. So let's try factoring a small number, 35 in this case. Dividing it by 2, we see that it's not an integer. By 3, well, still not an integer. Let's try 4. Well, we don't actually have to. We know that's 2 times 2, so if it were divisible by 4, it would be divisible by 2. And finally, we can try 5 and see that finally something worked. We get 7, and these are our 2 factors. The issue is that while we did it fairly quickly on paper, when the numbers grow, number of divisions grow really, really fast. We need to do around 2 to the n by 2 minus 1 divisions. So even for a 1024-bit RSI key, we might need to do 2 to the 511th division, or more than 6 times the 6 with 153 zeros in decimal. That's not a nice number. That's really not a nice number of operations to do. And this was a worst case. Even on average, we would need this divided by n times log 2. So only about 350 times less. And while usually you might be happy with 350 times optimization, 350 times faster operation, when you're dealing with such large numbers, this doesn't, this barely removes a few zeros. So it doesn't really. Because we're working in binary, so log2 is someone as y and log2. So this is kind of the issue that we have with a few numbers around here, because sometimes the algorithms are focusing on binary, sometimes they're dealing with decimals. So when you see log2, that usually means that we're moving between these two. Okay. So for practical computation, we're currently at exascale. So we have around we can do around 10 to the 18 floating point operations per second. I don't actually remember. I think it was FP16. Yes, 16-bit floating point numbers. So if we assume that we can somehow do a division in one FP16 operation, which we can, these numbers are too large to fit even in FP16. We would need a big integer for them, essentially. We would need over 10 with 115 zeros at the end times the age of the universe to factor this one number. So, are there better algorithms? Yes. Our current state of the art is the general number field sieve, or GNFS, and it only requires around 2 to the 86 operations for a 1024-bit key, which is almost doable. With our assumptions, it would be 4 months. In practice, it would obviously be years, so no one is trying. Our record is somewhere around 860 bits, and each bit doubles the efforts required. So, I mean, not doubles. As mentioned, the complexity is a bit smaller than that. But for 1024 bits, it takes 2 to the 116th. So this here is doubling. So 2 to the 87th would be twice the number of operations as 2 to the 86th. So twice the amount of time. 2 to the 116th is, counting quickly, 30 times, 2 to the power of 30 times more operations. So 30 times we need to double our efforts. That's not really practical for now. We need, like, even with very optimistic prognosis about our computing, this isn't something that can be practically done in like this century. And this is with being quite optimistic. We need a real breakthrough to get to that level. So finally getting to quantum. What is Schrod's algorithm? Well, we were thinking about factoring as dividing numbers or number sieves before, but let's try to move it to a different problem. If we pick a random number and then call this R, the order of n, where n is the integer we know. looking for? No, and sorry, it's the integer we know we're trying to factor. A to the power of r, r will be the order of a when modulo n, so divided by n, the remainder is 1. If we know this, we know that n will divide a to the power of r minus 1, because, well, when we divided a to the power of r by n, we got 1. And since we know this, we can use an equation that you probably recognize from, I think, even high school, I think primary school. But we can just divide it into you can just treat it as a difference of two squares, and get these two equations. So we know that n n divides a to the power of r by 2 minus 1 and a to the power of r by 2 plus 1. And we know that you can divide a to the power of r by 2 minus 1 because, well, the order was defined as the smallest a for which that would, as the smallest r for which that would be true. So if r by 2 was that order, we would have found it before, or we didn't do a good job order finding. So we know that a to the power of r by 2 plus 1 must could be divisible. Well, if it is, we actually haven't learned much because we just know that it's a larger number that has some other factor with n. You can multiply some other number with n and get that. However, if it isn't, this means that these two numbers must have a common factor, because otherwise this product couldn't be divisible by n. So since we know that n has only two factors, we can use Euclid's algorithm to find the greatest common divisor between these two numbers, which is quite fast, because it's basically basic arithmetical operations. And if we find p, then, like we mentioned before, because n has only two factors, we find q by just dividing n by p. So how does that help us? At first glance, it doesn't, because it's actually pretty slow. Order finding isn't fast, at least classically. Because it turns out that we can build a quantum circuit to solve order finding specifically, and that's what we'll be talking about. But first, short introduction to quantum, though you probably know it if you're here. Qubits are mostly about probabilities, so they are not or probability amplitudes. They're not like classical computing, where when you follow some steps, it's trivial to get the right answer always. Like, it's not necessarily repeatable. There is some probabilistic parts to everything. And also, you can change the probability of a given result, and that's how you actually do the calculations. Usually, we think about them in quantum gates, so we build circuits similarly to basic logic gates, but they're a bit more mathy just because they essentially require metric multiplication to think about. That's the easiest way, and they are all reversible, unlike classical gates. So if you there is an inverse that you can always get the initial input from a single gate. After gate, you can essentially always reverse a circuit. So for fast quantum order finding, we have Shor's algorithm. This algorithm is based on a quantum Fourier transform, which is somewhat similar to a classical Fourier transform, just, again, based on finding different probabilities. And we essentially apply a special transformation based on the next orders of our number. So, for example, this is the a circuit for factoring 15. We first have this matrix to get 7 to the power of 1, and this is controlled by the first qubit. Essentially, the ones at the top are control qubits first, just because there is a phase kickback. That is, some gates are controlled. So you get one qubit whose state can change the state of the qubit controlled by the gate. However, like logically, when you think about classical computing, if you have something like this is just an if, essentially. And the qubit that's in the condition wouldn't change. However, because quantum is a bit weirder, there is a thing called phase kickback where while the values don't change, the phase of a qubit, which isn't directly measurable, can change. And then we apply QFT and we actually throw away the qubits that we in theory changed. So we only, again, because we only care about the phase changes related to these operations, we only keep the qubits that were the controls, not the actually controlled qubits. And this is what we measure. In theory, with not it just to be clear, it doesn't work on always on the first try. It can require a few tries. But in theory, with just 2n+1 qubits and n to the power of 3 gates, we can calculate. We can find the order. So this is far faster. This is like linear. This isn't exponential anymore. So for RSA 2048, we don't need like 2 to the power of 86 qubits. We only need 4098 qubits and a few iterations. So when are we using cryptography if that's so easy? If you look at the roadmaps of big quantum vectors like IBM, you can see that quite a few have plans for computers with more qubits than this. For example, according to IBM, they should have a computer ready next year that could, in theory, break RSA. It has 4,158 qubits, or will have. So is it really the end? Well, fortunately, maybe. No, just because in reality we have a lot of noise. And in quantum computing, it's much harder just because we're dealing with so much smaller scale and effects that are really hard to measure. So there are a lot of errors everywhere. Every time we use a gate, there is a chance of a few types of error. Every time we measure, there is also a chance that our measurement will be erroneous. So we need to use quite a bit more qubits to correct for these errors and get actually reliable results. And unfortunately, that is many times more. Currently, Google's target is to get this small error rate, which for now to get just 10 to the minus 3 errors. So 1 in 1,000 qubits will have 1 in 1,000 operations will have an error. They are using 100 qubits for 100 physical qubits for one single logical qubits. And as mentioned, their plans to get to the actual scale are more like a few 100,000 to thousands of physical qubits for each actual logical qubit that can do any real work. So that's not great. This means that our 4096 qubit computer isn't even close to factoring large numbers, and our current record for factoring using Shor is 35, at least in theory, because that's actually very unreliable. So like we know it's 35 just because we actually knew the answer beforehand. We haven't factored a new number because I think like you would in theory need to get the right result more than 50% of the time. That this isn't it. There is very low probability of getting the correct results for 35. Our actually reliable record that we can get the right number for reliably is 21. And current state of the art when it comes to predictions is that to factor RSA in 8 hours, we will need probably something around 20 million qubits at current noise levels. So that was RSA. But what about other cryptography? Some of you may know that in many places elliptic curves are replacing RSA. Because they're actually quite a bit nicer for classical security. They're more performant, actually somewhat simpler, have smaller keys. They have a few traps, but this is what cryptocurrencies are based on just because of these nice properties. So what about ECC? Can we just replace everything with it? Unfortunately, it turns out that order finding is even worse for ECC. When RSA 2048 is equivalent to 28-bit ECC, it turns out that ECC of equivalent classical strength requires half the qubits as RSA. So you can see a few numbers here for simulations for how many qubits. Again, logical qubits, just to be clear. In reality, it will require millions. So what about symmetric cryptography? We were talking about asymmetric crypto, but maybe there is some way to attack AES or some other key other entirely symmetric option. Well, fortunately for us, while there is a way, it's not really that good. More specifically, it's possible to attack even symmetric cryptography by using Grover's search. That is a very efficient quantum algorithm that in theory has a complexity of around basically half the complexity and bitwise half. So actually, it's a square root of the length of our input to search it instead of being entirely linear. And it could, in theory, be used to brute force any cryptography much faster, of course, if we had large enough quantum computers. But in practice, especially symmetric cryptography, just has such large security margins that even like if we have it, it will be bad, but we can just use twice as long keys. Someone asked about towards lattice-based RFXE. We're mostly going towards lattice-based nowadays, but we'll see how that pans out. But I'll talk about it a bit later, in a few moments actually. So anyway, Grover works against anything, but it's not that good against anything actually. So it doesn't change that much for us. We just need somewhat larger keys and problem solved. So why use it when it's not really talked about, it's mentioned in all submissions for niche competitions, etc. But again, no one cares. We have security margins. We just build larger keys, larger crypto systems. So how about fixing everything? Turns out there are a few ways to build crypto systems that are resistant to Shor's algorithm and for now all no quantum attacks. More specifically, a few of these are actually quite old. And they're essentially a return to what we started our asymmetric journey with just after we discovered RSA. That just didn't stick around for various reasons. So, yeah, base algorithms will be covered. Let's first start with code-based algorithms. When you think about linear codes, I think many of you might have seen an image like this. This is a visualization of Hamming code. That is a fairly simple linear code for error detection and correction. It can detect up to 2-bit errors and correct a single bit error, though then you don't know the location of the other. And it's based on like a lot of things in cryptography, matrix multiplication. Most basically, like that's the simplest way to think about it. You basically can create the right matrices that when multiply it with your data will return a somewhat longer vector with additional parity bits. These bits can be used to check whether there was any error, any one of them flipped in transmission or somewhere else, and even, as I mentioned, correct one of them. This visualization is showing which parity bit covers which data bits. So, for example, the first parity bit includes in itself the data from D1, D2, D4, parity bit 2 from D1, D3, D4, and parity bit 3 from D2, D4, D3. That's how we can detect where exactly the error happened if it was a single bit error. And we can recover our original data quite easily. To be clear, recovery is here. This is how we encode data. So we encoded this vector by just multiplying it with this matrix. And then we can decode the original vector from the, this is error detection. So we can use the parity check matrix to find whether there was any error. And also, in case you notice, these are somewhat different matrices. Actually, like a lot of codes, Hamming codes, there are many permutations of these codes. So you can swap rows and columns and still get the correct code. So how to use linear codes for cryptography? Well, as mentioned, there are many codes for each of these groups. So what if we generated a linear code from some dark steric space and somehow used it, like multiplied it with some data, introduced some errors to make things harder, but without actually the person who does the encryption having the original code. That's the thought behind the Macalist crypto system. The idea is that we select a binary code of a given size, this is the NK, so that's the size of the matrix, that can correct up to, no, sorry, not up to, at least the errors. Just to be specific, that is, it will always correct the error, exactly the errors, but it can do more in theory sometimes. And typically, what we're using for this nowadays is GOPA codes, which are kind of codes. I think I forgot to put their equations, but doesn't matter. You can probably look them up on Wikipedia. It's not really that important for how this encryption system works. It works with other codes too. GOPA codes are just have some good properties for this. And we call the parameters that we use to generate this code A. Then we generate an invertible matrix as that is entirely random. Invertible just means that we can calculate its inverse. So we can reverse the operation of multiplying by it. And then we generate another random matrix, this time n times n, again square matrix. These are two square matrices. And this one is a permutation matrix. That is, it just changes the order of elements, essentially. Yeah, someone asked if the conclusion that number of qubits and quantum resources to crack its ecliptic curves is comparison with RSA was lower, even though it provided more security. Yeah. For the same classical security, elliptic curves require have the qubits to break. So for 128-bit security, so RSA 2048, you need 1024 qubits for ECC and 2048 qubits for RSA. And the reason you will actually see a bit when I talk about elliptic curves a bit more later. So we can compute this specific matrix by multiplying all of these matrices. So G is the generator matrix of the linear code. So like we've seen with having code, this is the generator matrix that can be used to generate the parametric matrix and basically a lot of the code. And by doing this, we're getting a matrix that can't be easily reversed into our original code. So this will be our public key. This is what we can share. While our private key is everything else that we can use to A, reverse this operation, so S and P, and B, generate our original code. Also, it's important to mention that N and K are known to both sides, so that's not we don't really care about that. That's public information. Then we encode the message as a binary string, and so a vector essentially, and multiply it when encrypt with while knowing the public key, and multiply it by this new matrix G hat. We can then generate a random binary string Z of length n with exactly T1s, essentially to introduce errors. And that's how we get our resulting ciphertext by doing this operation and introducing random errors to the result. In this way, when we want to decrypt things, we can essentially reverse things and use the error correction to decode the entire data. Because permutation matrix has countless places of bits, it doesn't really affect that much. But again, because the attacker wouldn't know the permutation matrix trivially, this is one step that makes things more difficult. But after that, again, because looking at the order, we need to do it from in reverse because matrix multiplication is actually directional, so you can't just swap things around. Then we decode, so essentially undo the multiplication by G. And thanks to error correcting properties of linear codes, because we introduced exactly T errors, we can correct them and get exactly what we needed. And then we just use the fact that our matrix S was invertible and get our message back. So this was a simple, really old scheme. This scheme is actually from 1977, if I remember correctly. So just a year after RSA. It's really not anything new, but it has recently returned as quantum computing has reached a stage where some people are worried. So now we have clustering Macalis. This is an algorithm that was in the NIST competition for standardization competition for quantum cryptography. And it's basically what we talked about, but with some efficiency and improvements, better parameter selection, etc. It's still using GAPA codes though, so that didn't change. The issue with all code-based cryptography though is that, well, everything is huge. Because we're dealing with really large matrices, our public key needs to be, this is for the lowest security level, by the way, equivalent to AES 128, so 128-bit security level. We need a public key of 261 kilobytes. Again, guess because there are no quantum attacks. There is no way to turn decoding linear codes into order filing, at least not efficiently as far as I know. So a lot of cryptography is unfortunately based on lack of knowledge. We don't know a way to do something. So Machiavelli is considered secure in post-quantum era just because we don't know any attacks that could affect it right now. However, when it comes to linear codes, they are actually considered quite safe when it comes to their security, other than attacks on some less common attempts, like newer attempts at defining different linear codes than, for example, GOPA codes, which are quite well understood. there hasn't really been any new attacks on Macalis, on any of the linear code crypto systems. So we believe they are as secure as they claim. Just because no one had any, for now, had any idea on how to attack them in a better way than mostly brute forcing the code. So the issue with that is, as I mentioned, cryptography is based around negatives here. So we don't even know if it won't turn out that literally all cryptography is unsafe. Maybe you've heard of P equals NP problem. If it turns out that P actually equals NP, so essentially problems that aren't, these are problem classes. Essentially, problem of NP class can be all simplified into P class, so polynomial problems. If everything can be polynomial, probably cryptography isn't really possible in a way, in a secure way, other than just making something really slow. But for now, we're assuming that things that we haven't no idea how to even start attacking are secure, just because, again, we haven't found a better way. As for classic Macalis, the issue is, as I started saying, key sizes, and especially the private key is literally megabytes in size. That is not something that can be used on tiny computers easily. Like obviously everyone on smartphones it can be used without problems, but if you have some microcontrollers, etc., you might start running into issues with these key sizes. And the performance isn't even that great. So it's not like it has huge keys, but somehow it's incredibly fast. It's slower. It's a bit worse than lattice schemes, essentially. So it is in theory a bit faster than RSA from my understanding, but not much. And also the bigger issue for example, TLS is that the ciphertext for classic Macalis, that is the actual data that we encrypt in every encapsulation session, is really small. So we can only send 96 bytes of data in like one encryption operation. So we would need to do, so this really hurts performance if we need more, because we need to do the same operation, for example, 4 times to get 4 times more ciphertext out. However, another fairly or someone asked the fact that we don't know much about protocol. That's actually one of the issues. The reason why these so many old protocols are now returning is that we actually do know quite a bit about them, but it got incredibly hard to prove in cryptography hardness of problems. That's because it's always possible that we missed some solution to a problem. For schemes like, as I mentioned, Macalis is considered quite secure because it's fairly well understood. We have studied linear codes for a long time. We understand how they work and their properties, just because we also need them for error correction, and because, well, cryptographers were also interested in that. But I will mention one of the issues with newer protocols a bit later. For now, let's get back to hash-based cryptography. Hashes, as maybe you've heard, are one-way functions. So especially they're really common in cryptography just because you often need to generate something from data in, for example, a pseudo-random function that is something that generates fairly uniform data from some input, but isn't easily reversible. So knowing the output, you can't get back to what you fed the function easily without brute forcing it. And it turns out that we can actually use it for cryptography. And this also is fairly old construction. I think first multi-use schemes came out in 1979. So again, This is 40 years in the making. Um, but the issue is that we start with something a bit simple because they have limited uses. One of the simplest schemes, Lambro signatures, is a one-time use scheme. That is, you literally only can use the signature once, and then you have to throw the entire public key, private key away because they're useless. They're not secure after that one signature. Uh, in this case, you start by generating 256 pairs of large numbers, so 256 bit numbers. Then you generate hashes of all of them via some secure one-way function. And then you hash your message, so the thing that you want to sign. In this case, as I mentioned, this is a signature function, so you want to confirm that you own some private data. It's important to note that at this point you should probably publish your public key because it will be used to verify that it's you. And if you publish it after the message, it's not really useful if you publish it with the message since it's one-time use. And then once you have the message, once you have everything at 256 bits, you go through each bit of the message, and for each one of your pairs of numbers, for each bit of the message, you have a pair of numbers, and depending on the value of the bit, you pick a specific number. So to verify that that the numbers you publish, that is the signature, match match your public key. You just to be clear, you publish the numbers themselves, not their hashes. So the original numbers. So anyone can verify by hashing the number that they match one of the hashes from your public key. So to verify the entire message, you just go through the message essentially in similar steps. You go through each bit and you check, but you just check that the hash that is in the signature matches the correct hash of the public key for that message, bit of the message. As you can see, it's fairly brute force, and you're essentially publishing half of your private key. So this isn't the most secure way of doing things. This is a one-time signature, and I'm not really aware of many contexts when it's used. However, this kind of one-time use functions can be used to build something a bit better. For example, Merkel's signature scheme is a multi-use scheme that allows you to generate n, that is to the power of n of number of messages that you want to sign, key pairs that are then used for one-time schemes. And also it has a nice benefit of using having a smaller public key. Mm, However, it has larger signature. You start with building a Merkle tree. Merkle tree is essentially a tree of hashes where you will start. You start with, in this case, you start with leaves. So you start with hashes of each of your keepers, if each of your private keys. The public key will be the hash them itself. And then you start hashing their concatenation. So essentially, if you look around here, for example, A10 is a hash of concatenation, so just going together A00 and A01. And you continue this until you reach your final node that is a root. This is also, you may recognize the name and the structure because it's used for example, Git and basically all cryptocurrencies. So to actually sign something, you select one of your unused keepers that were forming the leaves, that is that they were at the bottom. And you create a path by going up and actually selecting sibling of each of the nodes. So when you start from here, you go up. So this is the hash, and then you go to the sibling, so the one that shares the parent, and you take this number. This will be used later. Then you go up again, take the sibling, go up again, take the sibling, and finally reach the root. Then you create the signature of the message by using these siblings. First, you actually use the key that you selected. So this will be the one-time signature from, for example, the first number scheme. Then you, just to be clear, this operation is concatenation, so just adding together strings of text. Then you concatenate the public key you selected. So you are signing with private key. This is the hash of these numbers, probably, or whatever the scheme demands. And then you add all of these sibling nodes, not the actual nodes you traversed, but the siblings. And the reason for that is that you can verify everything by going up the tree. So when you go back here, because you have the hash, you have the public key here. So this is the public key, and now the verifier has this. They can again go up the tree by hashing the hashes together. Oh, and I think I forgot to mention that the root is the public key for the entire scheme. So this one hash. This is already better, but again, we don't have that many uses. We need to build huge trees, and it's fairly slow. So can we do things a bit differently, a bit better? That's where Sphinx comes in. The idea with Sphinx is basically taking Merkle trees and doing more of them. That is basically using seeded generators to create a pretty large structure of trees where the public key is just the final root of the final tree. This allows the whole scheme to use many more to sign many more messages than with Merkle scheme while using far smaller keys, because again the keys are actually seeds for not entirely random number generators, pseudo random function that is essentially hashes again. So this whole thing is just hashes all the way down. Sphinx Plus, the version that taking that actually is the finalist. I think this was a visualization of the sibling node. Yeah. So this is where you start with the message. This is the key you start with, and this is the path you take. So these are all the sibling nodes. This is what will create the signature itself. That's why they are grayed out. So like when we were here, it was visualized by the designs and the names of 0, of 1, etc. But this is more far out. I think also you can note that there are a few kind of nodes here. The squares are the one-time signature nodes. And the diamond is a specific kind of also signature, hash-based signature that was created for the purpose of Sphinx. But I would recommend the original paper for that. I haven't looked that far into how exactly it worked. But Sphinx,
Jakub, may I
Sphinx Plus,
interrupt?
yep.
Yes, there is a question from Kevin regarding these slides. Why are some nodes
Yeah, I
grayed out?
was just answering
Oh,
that.
okay.
Sorry,
Oh, sorry.
yeah, the sums of the squares and circles are grayed out because they're the path as we've seen in the previous in here.
Okay.
So when we marked things as off as the sibling nodes, we're doing essentially the same thing here. Because this was our message, we go through the entire hyper tree and take all the siblings to our nodes because we need them to reconstruct the entire not the entire Merkle tree, but the parts that are relevant to us. So we can go up the tree when we want to verify the signature. The nice things about the construction of Sphinx and Sphinx class is that, again, it can sign a lot of messages. The NIST level 1 version even can sign to the power of 77 messages. So that's probably enough for most purposes. The actual NIST requirements that the Sphinx Plus team got was to the 64, so they exceeded it quite a bit. The public key and private key are also incredibly small because they're the seeds, not the entire hashes like before, not large strings of numbers. And the signature is not the worst. It's 17 kilobytes, but around 20 kilobytes for NIST level 1, which is pretty decent when you consider some of the other schemes. But the issue is that hash-based cryptography is really, really slow because you need to reconstruct this entire structure. And it turns out that secure cryptographic hashes are unfortunately fairly slow. And even the first one can be somewhat problematic. For example, there is actually an attack on Sphinx plus NIST level 5 version that uses specifically SHA 256 that decreases its security to, I think, to the power of 217 bits from the claimed to the power of 258, if I remember correctly. So this is still basically not practical to attack, but something about the construction of SHA 256 meant that the security of the scheme was greatly undermined for that specific purpose. But again, this was got specifically about SHA 256. As far as I know, this kind of attack doesn't apply to the other hashes they chose. They actually have a specific hash for the signatures that produces, from my understanding, can produce somewhat smaller signatures and was tuned specifically for this purpose. The SHA-256 and SHA-3 versions are mostly because NIST wants to unify their cryptography. But well, it mightn't matter anyway because, as mentioned, they're incredibly slow. Even the NIST level 1 version can take around 1 second on Raspberry Pi 3, which, well, isn't a top-level computer, but like, it's not some microcontroller. It's not something incredibly small and uncapable. So a second for signing is just terrible. Usually you're thinking about tens of milliseconds or maybe 100 milliseconds. But no, you get 1 second for to sign and verify a message, and most of this is actually a signing, which is like pretty bad because if you are generating key for a long time, that's not an issue. You might do it once and then sign many messages. But if it's signing or verifying, then that's problematic. Though fortunately, verification is fairly fast, so at least it's only the sender that has problems. So moving on to something quite a bit newer, because we're talking about crypto from the 70s. This is essentially cryptography from the 2000s. It's the much more recent addition. And it starts with elliptic curves, the things we talked about it before. So to set background, elliptic curves are essentially the simplest way to describe them is this equation. They're not really some arcane construction like the name might suggest. They're just curves. However, they have few nice properties. The most important of which are the operations that can be performed in them, and especially point addition, because a non-vertical line will intersect the curve at most 3 points. 2 points can be essentially added to create a third one. That's always unique. There are also other operations that are related to using specific kind of lines or points. and there is a point that is the identity of the group. So elliptic curves essentially can create a mathematical group with that's useful for some algebraic purposes. So when we look at signing or encryption, to be fair, with traditional ACC, we essentially generate yeah, I will get to the second in a bit. I just want to start with elliptic curves, the basic ones first. So first we start with a random integer, that will be our private key. And then, just for some nice services, we actually hash it and we use the least significant bits of the hash to calculate a new point from a basis point of the scheme. This B is specified for is in the specification of a given scheme. So, for example, ED25519 will have a specific basic point, and we multiply this point. So add it to itself, like we've seen here. If you have something like this, this will be adding the point to itself, finding a new point based on the gas itself. As times. So again, as we were thinking about them as vectors before, now they're just numbers, just to be clear. And this A, this new point on our elliptic curve, will be our public key. Then using a public key, we can create a new point by essentially solving this equation for S. We can choose R, which can actually be somewhat problematic, but I'll mention it a bit later. And we then we need to solve this equation to get S. Using private key, it's basically fairly similar. We also can, though we use the hash and the message. Again, these are concatenations. M is the message here. R is the point. A is the point. That is the public key. This is signing using elliptic curves. As you can see, mathematically, it's actually fairly simple. While the equation might be a bit intimidating, the whole operation seems actually quite a bit simpler than some of the earlier signing schemes, especially the hash-based one. But more important one is probably key agreement. So this is specifically a protocol for creating a shared secret. So for example, a shared symmetric key. This is what's commonly used for example, TLS also. So here both sides again use a random integer. Here we have communications from both sides because there is an agreement. And multiply a common point G. This can again be specified or can be negotiated for a specific session. And multiply their integers, their private keys by this point. Multiply their point by this integer, so just add this point to itself that many times. This way they get two keepers, the points, the new points that they get the Q, and their private key, that is the integers. The public parts, so the Q points are shared with each other, and they can just calculate the common point by just multiplying the new point by their own private key. This way, as you can see here, because multiplication works, in this case, you can actually swap the numbers here. This is exactly equal, and they get a common secret. Usually, we pick X, which can sometimes be problematic because we're essentially discarding one dimension here. And if the programmer ignores it, from my understanding, an attacker can actually you can get into some trouble with some specific instances of forked data in the attacks. So this was pretty simple. Again, this is probably the simplest scheme I was talking about. For now, you basically have multiplication in this weird elliptic curve group, but that's just all. You just add points I guess follow the formula here formulas here to get the points. And that seems very simple. There is a reason why it's so common, why people are moving to ECC from RSA. Because again, it's simple, it's fast, the math is nice. There are some traps with weird points, with not thinking about about checking specific points, etc. For example, in ECDSA, if the point R is a 0 on the curve and you don't check for it, from my understanding, you can get a correct verification that doesn't check for the point being a 0 of the curve. Will get returned true no matter what the signature is otherwise. And that was simple, but because you can see that we have the order finding, we essentially all points have their own orders. So when you go back here, you can do that. You can do addition. You can add point to itself many times. But at some point you will reach a 0 of the group. So essentially, number that does that doesn't affect multiplication. So this is something that useful for some purposes. Limits the size of integers. For example, the integer k has to actually be smaller than the order of the base point for that reason, because otherwise you're looping. But it means that the whole scheme is based around some order of some much smaller order. So that's why it's easier to use order finding to break EC than RSA. But finally, for the supersingular part, supersingular elliptic curves are actually gas elliptic curves. The name is scary, but there are just a few conditions. More specifically, invariance, that's a specific property of elliptic curves related to their complex numbers and their conjugates. And that's where they have singular points. Points of singularity. However, ironically, the curves themselves are non-singular, so they don't have singularities themselves. They're actually lines, so points of singularity would be breaks. And isogeny is the other part of the whole supersingular isogeny equation is actually just a function that maps from one curve to another curve while preserving many of their properties. So more specifically, it needs to have a finite kernel, and it will map into another elliptic curve that is also supersingular. So that's how you end up with SID. You essentially generate, again, two random integers, generate points this time because there is this time you used two basic points. This P and Q are given for the scheme or session. And then you create an isogeny. So you move your entire work to another curve. There is an algorithm for creating isogenies. I think it was Ballet algorithm with preserving a kernel in these points, which matters for security reasons. But what matters to us is that it's essentially just a function that can transform a point from one curve into another curve, move it. And then you send the new data needed for the new curve. And the points you had transformed by isogenies, actually points reversed. So PA and PB are both given in the scheme or in the session. So you use the isogeny to transform. If you're A, you use the isogeny to transform point B, and if you're B, you use the isogeny to transform point A. Then you calculate things again with your integer, so similar to our ACDH before. And because we're using isogenies, you just create a new isogeny for the new point and get a new curve. This time it won't be a point that's common, but instead it will be the curve that's common. So both parties will get the same super singular curve because they get the same isogeny from E. This is isogeny that will transform E itself to the new curve. And I mentioned that the supersingular part is to gain variant. I would have to look up a formula for calculating that, but generally you can just treat it as a specific function for supersingular curves that will give you a number. Uh, the, and the important part is that it will be constant for a given curve. And that's how you get the short key. Essentially, the short key is actually kind of the new curve itself, not the point that created it. The issue with SID is that it was entirely broken. It turned out that you can recover the key from listening in from any middle attacks in just a few minutes on a laptop. So this is the danger that when people are asking about unknown cryptography, that we don't know the dangers of it might turn out that things are broken, but we just didn't know. SID turned out to be entirely broken, and it's just lucky that this was an attack specifically for this scheme, and it isn't generalizable for now, at least, the entire category. But as you can expect, this means that supersingular isogeny is got quite a bit of bad press. The simple implementation that was nice, that mirrored ECDH that's used everywhere, but just promised to be quantum secure because of the isogenies not being vulnerable to order finding attacks, turned out to be broken not without even having to use quantum computers. And while there are still a few singular isogeny, super singular isogeny based schemes, the attack doesn't apply to. I don't think there aren't that many teams that are eager to try their hands with super singular isogeny anymore, from what I've seen. The only real candidate for this additional digital signature scheme that's currently running it's SQE Sign, that promises quite simple verification, but again has very small keys and signature sizes. But also has the issue that hash signatures had with very slow signing. And well, yeah, who knows? Again, it's fairly new cryptography. It may turn out that it's also horribly broken and it's unusable in practice. Now, finally, to the lattice schemes. First, again, a bit of a very simple instruction to what are lattices. The simplest way to visualize them is just integer. If you had a vector field or just two number lines or multiple number lines, got to be precise. You had some vectors on them, and you only took the whole combinations of them. So essentially, these are integers for vector fields. Instead of getting some part over here, you always combine the entire vectors, or their negatives, obviously. The nice thing about them, is that there are a few fairly hard things to do in lattices. Most importantly, the shortest vector problem, because it turns out that for any given lattice, you can actually create multiple, again, not pairs, multiple sets of vectors, basis vectors, that will create this exact same lattice. However, there is a shortest set that is the set that's using small, well, kind of obvious what shortest means. So a lot of early lattice schemes were based on essentially reducing the lattice, finding the shortest vectors that define a given lattice. However, another problem related to vector length would be cross vector problem. In this case, you have a lattice that's somewhat defined, and you need to find a point that's closest to a random non-point that isn't on the lattice. These are both hard calculated problems. However, important note, not on 2D. What I'm showing here is it's trivial to do. As you can see by the visualization, that wouldn't be hard to brute force. However, in reality, you use lattices of really high orders. You use, for example, 40-dimensional lattice that's actually fairly small, or if you 100 dimensions. And however, the nice thing about lattices is that while this is a nice visualization, in practice you're usually dealing just with equations. So uh, not equations, but multivariate. Uh, so anyway, another lattice problem, a problem that's related to lattices is learning with errors. That is recovering a secret given a sequence of approximate linear equations. This can also be moved to lattices, or most specifically, it will be there on a ring, so on integers. And the whole point is that you basically get equations that don't result in integers. You get in case of lattices, this would be again lattices are like integers for vectors. So you get lattice points that are integers approximations. But in reality, the values aren't on the lattice. Kyber is one scheme based on learning with errors. It's the current winner of the NIST competition, and it has pretty nice properties. The key sizes aren't terrible. They're not the best, but they're bearable. A few hundred bytes below 1 kilobyte for public key and cipher. Ciphertext is fairly large compared to, for example, MacAlice. And the private key is 1.6 kilobytes for, again, this is level 1, so this is 128 equivalent. And it's fortunately fairly fast, faster than RSA 238. So that's nice. Though slower than ECC, I think. I would describe everything, but the thing about lattice schemes is that they're kind of when you looked at the previous schemes, you've seen what they're based on immediately based on the operations that they were doing. I can explain that this operation is basically is adding the point to itself multiple times, for example, for elliptic curves. However, for Kyber, everything will not look like lattices. Essentially, you have groups and sampling on groups, so random processes, and then a bit of vector mathematics. So that's not really easy to conceptualize. And this all can so composes itself into a fairly nice key exchange function. But again, you need to look into the specific functions and do quite a bit of work to visualize them, what they actually are on lattice. I actually, as someone who actually implemented Kyber into separate programming languages, I have no idea how specifically it looks on lattices, to be honest. The issue with lattices is again, as was mentioned, we haven't studied them as well as RSA and ECC. They actually lost a bit of their security over time. Some of our assumptions turned out to be false. They're still considered to be fairly secure, and the strongest assumption that like the way the schemes in, for example, in this competition work, they take really pessimistic views on their security, fortunately. So, for example, Kyber and TerraU and most other schemes are using a metric from another scheme called Lightsaber. No, Sorry, New Hope. Too many Star Wars themed schemes here. New Hope. That's called core SVP. That essentially is the worst case if the entire scheme could be broken with a single shortest vector problem oracle. So if someone could solve a shortest vector problem on a specific large lattice for a given scheme, just once, the scheme will be entirely broken, which isn't actually true. This is the assumption they're going for their security calculations. But in reality, even if the learning with errors assumption that prevents just doing the shortest vector problem trivially was false, which they're assuming, the calling the oracle for shortest vector problem would require, I think, also polynomial invocations. So in reality, you need many, many times more invocations than just one that their current assumptions are working on. So, as mentioned, the current state is that Crystal, Kyber, and Elysium are on the finish line to standardization. The standard are essentially already published or preview. There were some changes in Kyber, for example, when I mentioned speed, there was actually a bit of a speed bump in key generation that ended up being removed from the standard because it was a bit embarrassing for NIST and was sometimes called the hash of shame. Essentially, Kyber authors decided to hash the output of a random number generator, which, if you think about it, doesn't make sense because you just use the pseudo-random function on a real random function to get the same number of bits in this case, literally doing no useful work. But the reason was, I believe, a critic of NIST, which was found to have backdoored a random number generator in 2009. That fortunately wasn't commonly used and isn't at all in the standard anymore. But it really left a stain on its credibility. And as we can see, even on standards that are created. Currently, Kyber is the scheme that seems to be implemented the most. Browsers are rolling out TLS. I think Chrome production version already has, and Cloudflare supports it. So potentially, some of your TLS connections might be actually using Kyber already. But we're mostly doing that in a incremental way. So we're adding encryption on top of existing classical encryption, again, because we're not entirely sure about our assumptions for security of the new cryptography. And Signal also already has Kyber-based message encryption, again on top of classical elliptic curves, and also their scheme is in theory not quantum resistant against an active attacker. So if someone has access to a quantum computer and can listen in on your communication, they could break it. But if someone listens in now without a quantum computer large enough to break things, which no one has nowadays, obviously, and saves that message for the future, the new scheme protects the message from the quantum attack. So basically, we're starting to switch. We're still not really sure about things, but they're good enough at least. There were already years of research on all of these schemes. And especially some of the older ones are fairly well understood, and there weren't really many surprises for them in the competition. But as mentioned, there were some speed bumps. Around three finalists of the NIST competition, so it got through quite a few tests and got quite a bit of scrutiny. But Rainbow was broken in a weekend on the laptop. And despite that, the author still believes that it's the best cryptography scheme from cryptocurrencies for some reason, which I don't think anyone gets other than them. And as mentioned, Psych or SID was also horribly broken, and and it actually was selected for round 4. So essentially, again, NIST also is very conservative about these schemes. So because for encryption for Clear only a lattice scheme was the finalist, they want to have some alternative options. So they moved some schemes that weren't using lattices to round 4. And that's still going on. But as we can see, Psych was removed from it entirely because it was just broken horribly. Uh, and actually, if you if you go to their paper on this site, you will get a paper that only says that the scheme was removed and it's not recommended because it's insecure. So one question would be if we could increase the size of symmetric keys to make them resistant uh, to quantum attacks, that is, Gauss-de-Grauber search. Can we make RSA better? Well, we actually can. One of the submissions to NIST was RSA with multi-gigabyte keys, and it works. If you just have a few hours or a few hundred hours on your hands for each encryption, it might be nice. Uh, Obviously, you can make RSA harder to break or move the deadline by just increasing the key size again. But if you're expecting quantum computers to grow at really fast rates, it wouldn't really be practical to just increase key sizes of RSA or RSC, unfortunately, because to get the equivalent security that the NIST competition requires from their entrants, RSA would need really huge, just unbearably huge keys that the authors of this paper didn't even actually manage to generate in the end. Uh, so go ahead. And as I mentioned with Signal, there is another problem. That is, even if we're switching to post-quantum cryptography now, or some people might have already saved the messages, the encrypted messages that weren't using post-quantum cryptography. So that's basically the trivial attack, the like trivial way of attack. If you're just very patient and if you have data that might still be uh, important, that someone might still want to decrypt in 10 to 20 years, or maybe even more, who knows. You probably might want to start switching to post-quantum cryptography or at least post-quantum envelopes for classical cryptography sooner rather than later. These people, uh, Nibo asked if these people give rigorous security proofs for each protocols if they claim to be secure. So if they can get advisory game. The issue is that RSA doesn't have proof, actually. Basically, there are very few protocols that have rigorous security proofs when it comes to cryptography itself, because it always goes back to the assumptions. You get protocols that have fairly good proofs that as long as their assumptions hold, they are secure. But these assumptions aren't necessarily true. For example, I believe that Kyber, if learning with errors holds, it will be considered as secure as it claims to be. Even more secure than it claims to be honest, because again, the core SVP. But we don't know if learning with errors is actually not solvable more easily, and it's somewhat doubtful. Again, there are some attempts. It's something that I think was actually the cause for loss of some security for lattice schemes, that learning with errors got somewhat easier. The same can be said for basically all of these schemes. Uh, and most don't actually have rigorous proofs that they're as hard as their assumptions. I'm not even entirely sure if Kyber does. Yeah, Diffie-Hellman also doesn't have proof. Rabin, signatures, so similar to RSA, does have security proof that it's at least as hard as factoring, if I remember correctly. But again, that doesn't really help in this case. RSA also has the RSA assumption that could, if broken, could in theory make it even easier than just factoring the numbers. Though again, this assumption isn't, and this assumption isn't really as rigorous as factoring. We don't know if there isn't an easier solution. So a lot of cryptography is unfortunately built on us not knowing things and assuming that we will not learn better ways to do number crunching. So for these better ways, I mentioned at the start there are a few new factoring methods, and Shor's algorithm isn't the only one in town anymore. For example, some time ago there was like last year, technically even in 20, even 2 years ago, in December, so, at the beginning of last year, there was a claim, actually a paper published by Chinese researchers claiming to be able to factor integers with sublinear resources, which sounds like incredibly good. We were talking about exponential functions and maybe polynomial, but now sublinear. That sounds incredible, or like terrifying if you actually want things to be secure. And the whole idea is to, going back to lattices, move factoring into a lattice problem, actually closest vector problem. But the idea is that you can craft a lattice with basis of decently small dimension with specifically chosen basis vectors that allows you to create a set of linear equations that are so fairly easy to solve and can get you the one of the factors in the end. The quantum part was actually optimizing this lattice, so finding minimal energy solution and then solving the actually closed vector problem. Again, it's a closed vector problem is a hard problem, but if you just get the lattice small enough, it's possible. But the issue is that we've seen this exact claim before. This is a Schnorr's, not related to Schnorr at all, actually, despite them both being named Klaus. Also, but this is a publication from 2020 that claimed to break RSA classically, or literally in the abstract claim to destroy the RSA crypto system, except that it didn't. The idea was that it would allow to factor even 400-bit integers with just 47-dimension lattices and 800-bit with 95-dimension lattices, which are things that are doable. As mentioned here, 8.4 times 10 to the power of 10 arithmetic operations, which is a lot, but compared to the numbers we've seen earlier with 100, more than 100 zeros at the end, this seems trivial. This would actually be doable on current hardware, except if you try to run any of the implementations that actually were made of this algorithm, which the author never did, from my understanding, never implemented it. It turns out that the whole scheme relied on the assumption that certain properties of the lattices it created would be common, and they just don't seem to be. From my understanding, it's not really, it's essentially not clear why this doesn't work, but it's also not clear why these lattices would be common. So essentially, the author assumed probably that he manually calculated. So my guess would be that he calculated some at some attempts, and the lattices worked, but when moving to larger numbers, they just turned out to be much more rare than he believed, and you actually will have hard time factoring a 40-bit integer with this method, which if you try with more classical methods, turns out happens instantly. I think I ran to be fair, a Python version of this algorithm for like an hour and didn't manage to factor a 40-bit integer. So that's terrible. And well, it seems that the quantum version isn't much better. The whole idea behind it was that again it would optimize the lattices. So again, the hope was that uh, the lattices that actually have the SR pairs that are required for creating these linear equations would be much more common with these optimizations, but they don't seem to be again. This is an attempt at this is mostly commentary on the paper, but also an attempt at verifying some of their claims. Um, and it finds again that it quickly becomes impossible to factor things. It goes a bit higher than what I got with Schnorr's paper, but probably also a better implementation of Schnorr classically would work. Which, actually can be seen here that they literally brute forced instead of using the quantum method and got better success. Uh, so a few months ago, there was also a pretty interesting claim by a researcher that actually published a few papers with Rifest Shamir some time ago, but recently seems to be a bit on the deeper end, with even claiming that he broke RSA with via quantum computing on the phone. And even not just RSA, but 10 to the 1000 decimal digits cryptography, whatever that would be. Uh, but he didn't publish any numbers. So, you know, if someone happens to be on the uh, in a moment, if someone happened to be on the verge of solving solving factoring numbers and essentially all of computation, like revolutionizing personal computing, they would probably try to at least publish some proof, not just a paper that claims to have proof but never delivers. Mm. But there are also more slight improvements, more maybe not slight, but more reasonable improvements. One of them is, yeah, as someone mentioned in the chat, a regex factoring algorithm uh, that essentially at first just moved a bit of complexity from mostly from the circuit size into the number of qubits. However, this was actually optimized later, which turns out to beat Shor on both counts. Though it still require. I don't think anyone actually. I don't remember that this paper having numbers for how many qubits it would, like how many physical qubits it would take for to factor uh, RSA 2048. And unfortunately, calculating that isn't as simple as just multiplying things together, because you have to take into account also quantum volume, like how many, and a bit of issues related to noise that just aren't trivially solvable, and maximum circuit sizes on specific computers. So that's a bit harder topic, but yeah, it seems like it will be an improvement on Shore. And while I don't think it's like numerically it's some huge revolution, like suddenly going to maybe we'll do it in a few years, in 2 years or something. It does mean that the race is more closer on. We're not just building bigger computers, but actually finding ways to use the ones that we have better. That's one of the reasons why I might be more worried. Another is the rise of using quantum computation by measurements, which in this case, this paper here is about the idea of essentially saving Shor for later. So if you can factor if you can use Shor at some size, the quantum measurements method allows you to essentially save your calculation for later and reuse them in really short time. So if we could factor Shor for 2048-bit integers once, In theory, by using this method, we could create a dedicated quantum circuit that solves 2048-bit RSA in now much shorter time by just measuring numbers, measuring photons. So what should you do with this? As mentioned, don't panic. Breaking decent RSA is still likely more than a decade away. The roadmaps really show like the roadmaps are mostly followed, but even by them, we're not even close. We will need a few hundred times more qubits than we already have. And you probably shouldn't speak everything to post-quantum cryptography just yet by just clamping the ship, because it may turn out that even Kyber goes the way of Psych, and maybe we find some way to solve the problems it relies on, uh, or maybe we just find some glaring implementation issue that we somehow missed for a few years. This is a bit less likely with schemes that we've studied for longer time, like classic Macaulay or things that's based on uh, quite well understood hashes. But it may be still worth to add post-quantum cryptography on top or well below standard asymmetric cryptography like elliptic curves or RSA. And also claims of any algorithm that seems to be incredibly better, like sublinear or maybe factoring, or maybe to say that you can factor RSA 1 to 24 with just a few hundred physical qubits or something like this. This should really be viewed with a lot of caution. As we've seen, there were a few examples of extreme claims and they didn't seem to meet scrutiny. But that doesn't mean that we're not getting better. Uh, as I mentioned, quantum blenders are at least seem to be outpacing their own timelines a bit, though they aren't that actually that fast if you consider how things went with classical computers. And the level of investment in quantum technologies seems to be increasing. And well, we're in an AI boom, so quantum AI is also a buzzword that might drive some investment. And as mentioned, we're improving the algorithms too. Um, so even if the level of improvement in the computers themselves might not be at as fast as to endanger our computers in a decade or two, maybe we'll improve things enough that in 20 years we'll be breaking RSA on quantum computers already. Guys, don't expect to wake up to Q-Day, the breakage of all RSA, all ECC just yet. So thank you for your attention. Any questions? Any additional questions?
Okay, great. Thank you, Jakub. Thanks. A very interesting presentation, and also thanks for answering the questions that we had during the talk. There's another question from Muhammad Reza. Is it a good idea
Uh,
generally to devise higher levels of security based on the methodology of the attacks themselves?
uh, what exactly? I'm not sure what exactly do you mean.
Maybe you can
We're
clarify, Muhammad
mostly,
Reza.
uh, if you mean, for example, Grover search, like which I don't think we really have moved things that much. As I mentioned, a lot of cryptography has very good security margins. There were actually people who were arguing that our modern cryptography has far too big of a security margin, and that we should actually make it just more performant by, for example, decreasing the number of rounds in AES. Uh, um,
Using QM in a systematic way other than heuristic methods, if it makes sense.
uh, do you mean like trying to create a higher level of security by assuming that there will be a quantum attack on the scheme that we guys don't know about, or
Mohammad Reza, maybe you can unmute yourself and clarify as well.
uh, the
Mhm.
issue with this is that quantum computing is fairly difficult, and we haven't found ways to apply it universally in most cases. Like I would say that Grover search is one of the more universal algorithms that actually seems to work. So the when trying to devise defenses in a systematic way against basically a possible new approach, you run into the issue that you might again create some extremely huge security margin that in the end cost hurts performance, cost hurts usability without actually solving any real problems. Or on the other hand, it might turn out that you severely underestimated things. And for example, as with SID, your whole the issue with SID wasn't that uh, they didn't have big enough security margins. The issue was just that they missed some way of reducing the whole scheme to a much simpler problem. Uh, and that's something that what I, what I've seen is really hard to systematically eliminate. That's because again you're dealing with mathematical ideas essentially, not with not with anything systematic. That's just finding new ways to uh, do specific math or
Mhm.
optimizing the existing ones. We can obviously try to predict how existing methods will improve, and that's what we are actually doing. From my understanding, the NIST competition was actually requiring all schemes to also mention their complexity under Grover search, for example. And the security levels were also based on on the assumption that Grover search works. I hope that answers your question.
So, so I just wanted to say that it is my understanding that almost all of these PQC methods are classical in nature. They are not based on the laws of quantum mechanics, if it makes sense. I don't know. So maybe if it is a general question. If indeed it makes sense to devise security measures based on the methodology of attacks. So, for example, quantum mechanics in this case for post-quantum era. Yeah, that was all of the question. I mean, maybe it does, maybe it doesn't.
Again, the quantum attacks aren't I think I get what you mean that they're classical in nature, that all of them do have classical parse or counterparse. For example, you could in theory try to implement something like sure in classical computing it will be just slower. Uh,
Yeah.
but the issue is that we specifically are finding ways of optimizing the things that didn't really seem to make any sense under classical computing. Uh,
Mhm.
for example,
Mhm.
if you tried to do if you tried to secure something against using Fourier transforms for order fighting, you would find that people would laugh you out of the room. For sure, came with his idea, just because Fourier transforms are really slow. Why are you optimizing for something worse than what you already have? Like there wouldn't really be an obvious way to do that.
Okay, thank you.
If we try to have systematic ways of addressing every possible way of turning one problem into another problem, I would again run into the issue that it's basically impossible. You don't really have a way to devise a scheme that can be transformed into other problems and can't really check all of them.
Mhm. All right. Do we have some other questions? Maybe there are some unanswered questions on chat.
I think I was
Okay.
answering
Yeah.
them as we went on.
Yes. Yes. I think so. All right. So yeah, thanks, Jakub, once again. Thanks also everyone for attending and answering interesting questions. And Jakub, thanks uh, for the answers. Maybe before we finish, I will just share a few last slides just to announce our next meetup. All right. Let me maybe just go to this full screen mode. All right. Yeah, so once again, we thank our strategic partners, Colgate, Onyx Alpha, R&D Sonovero, or Sonovero R&D, and ThinkQbit, and our honorary partners for supporting us. And the next meetup will be probably in March, and Krzysztof Kuba, who is also a member of Q Poland, will tell us about building quantum computers, especially about the physics, because he studies physics at the University of Warsaw. And if you like our events, let's stay in touch. You can join our mailing list, our Facebook group, follow our fan page, YouTube channel, X or LinkedIn profiles as well. So let's stay in touch, and then you'll be informed about the next events. Okay, good. Thank you once again. Yeah, I wish you a good evening, especially to people from Warsaw, and great and successful year, because this was the first Warsaw Quantum Computing meetup in this year, and we hope to see you next time. Thank you once again. Bye bye.